Welcome back to the Organic Chemistry playlist. In this episode, we're going over some H NMR problems. And in this example, are these four molecules that I have here. I'll just showcase them. I'd like you to, first of all, tell me how many unique hydrogen NMR signals that we have, but also the multiplicity of them. How many is it going to be, like a singlet, a doublet, a triplet, etc., that kind of thing. So let's go through all the problems now. So first I want to look at how many peaks we have, so that will be important. So notice there's no real symmetry in this molecule, so each carbon where there's a hydrogen, it's going to be a different environment. You might be looking at these two ethyl groups, and you might be saying to yourself, well, hey, that kind of looks symmetrical. No, because this ethyl group is one away from the anisole ether little bit there. This is an ether right here, so notice how it's in its own environment when relative to this ethyl group, which is just 2 carbons away, not just 1 carbon away. So that's the difference, and that's why there's no symmetry. That being said, we know that this carbon here has 3 hydrogens, and that will give rise to a signal. This carbon doesn't have a hydrogen, so we'll ignore it. We have a single hydrogen there, 2 here, 3 here. Notice we have 1 hydrogen here, 1 here. No symmetry, so they don't get their own respective signal. We have 2 hydrogens there and 3 there. So if we count the number of unique hydrogen environments, it's 1, 2, 3, 4, 5, 6, 7, 8. So for the first part of the question, and I'll just write this in a different color, we're going to have 8 signals. Okay, so now that we identified that we have 8 signals, now let's look at how many is it going to be, the multiplicity of it. Will it be a singlet, doublet, triplet, etc.? So to identify this, you need to know the number of neighboring hydrogens and then add 1 to it. So for example, this group here, there's 3 hydrogens giving rise to that signal. However, there are no neighboring hydrogens. The only neighbor they really have is an oxygen there, and that's not a hydrogen. So we'd expect a singlet, and I'll just write 1 for this. So writing in the blue here, that's the multiplicity of all of these respective groups. Next door is only there's nothing next door. It's only an oxygen, but remember it's n+1. That's that rule there for NMR, that the multiplicity will always be the number of neighboring hydrogens plus 1, and I'll just write that out, n+1, n+1. So keep this rule in mind right here. So looking at this respective environment, we have 1 hydrogen, and it seems like it also has no neighbors, so it will also be a singlet. So we'll write 1 there. Right here, how many neighbors does he have? Well, he has 3 to this side of him, and then he goes 1 carbon over, and there's no hydrogens there, so this will be quadlet? I don't know, 4. There's going to be 4 respective multiplicity peaks there, because there's 3 neighboring hydrogens, and then we follow n+1. That gives us 4. Here, it's quite simple, right? There's 2 neighboring hydrogens on this group here, so that's just going to be, nope, not a 2, a triplet. It's going to be a triplet. These carbons are quite simple. We can kind of treat them as the same in a way, so to speak. They're their own respective hydrogen environments, but what's their multiplicity going to be? Well, they only have 1 neighbor, so they're going to be a doublet, respectively, right? n+1, 1 neighboring hydrogen, right, for each group respectively, and then n+1 just tells us there's going to be a doublet there. Okay, so we move on to this carbon right here. It's kind of the same diff with the other group. There's three neighbors, n+1, that gives us 4 total. 4. Awesome. And now we go over to this final one. Same diff, and that's going to give us 3. Hopefully that makes sense. So we're going to get 8 signals, and the relative multiplicity of all those is given here. All right, moving on down. We have, what would that be? 1, 2, 3. 3-methyl anisole. So let's do the same thing here. This is its own respective environment. Notice how we have a plane of symmetry going through the molecule like so. So when we compare 2 hydrogens here, these are homotopic to these hydrogens here. So that's important to keep in mind. So this is a respective hydrogen environment. This is a respective hydrogen environment. And of course, we have these methyl hydrogens on the end. So now we know we'll get 4 peaks on our H NMR. Oh, that handwriting is terrible. Jeez. Okay. Well, let's get into the multiplicity now. This guy here has no neighbors. He's a lonely little guy, so he's just going to be a singlet. Notice we have these 2 homotopic hydrogens. They both have, this carbon has 1 neighbor, this hydrogen here, and this carbon respectively has a neighbor there. So that's 2, and plus 1 tells us for this group of hydrogens in that environment, we are going to get a multiplicity of 3. Same with this, right? So these 2 hydrogens have 2 hydrogen neighbors, and plus 1, that's just 3. Quite simple, hopefully. And then on the end here, they have no neighbors, so they will just be a singlet. All right, now moving on to this molecule here, 2-bromopentane. Let's first identify the unique hydrogen environments. We'll start with the easiest one. This here is its own respective environment, and this one here as well. They can only be homotopic, and not homotopic to each other, but just homotopic respectively, right? Because they can't be, there's 3 hydrogens here, and even if we did the replacement little gimmick, wouldn't really work there because we would not have a chiral center. So those are their own respective environments, and also there's no symmetry, so they are not homotopic to each other. So notice that this carbon here has a hydrogen, and that will give rise to its own signal. So that's a respective environment. There's 2 hydrogens here, and remember that little gimmick, replace the 1 and see how they relate. So if we were to call this molecule, if we just had hydrogen and we called this A, just a random variable placeholder, we have an A group there. Notice that this forms a chiral center, but it's going to also form a diastereomer, right? Because that bromine is stuck on the wedge and we can't form enantiomers, we can only form diastereomers. So that makes these 2 hydrogens diastereomerically topic to each other. I'm fucking butchering that, but that's all right. So this will give rise to 2 respective signals. Oh, brother, I'm struggling here. 2 respective signals, and the same goes for this hydrogen using the same logic. So they have their own respective peaks. Now we have to describe the multiplicity of these, right? How many times is it splitting apart in that signal? We remember we have to use the n+1 rule. So that's the number of neighboring hydrogens plus 1. So this here, this one has 3 hydrogens on it, but it only has a neighbor that has 1 hydrogen on right here. So this will be a doublet. This here will be a doublet. Notice this here, we have 3 to the left, 2 to the right. That's going to be whatever a sixlet would be. Sorry, I'm not too good with my numbers, y'all. No bueno. Let's skip these for now. These get a little tricky, but we'll get into it. There's three hydrogens here in this environment, but they have two neighbors, so this is whatever, or a triplet. I almost didn't know what that was, and that would have been fucking embarrassing. Okay, so we have a hydrogen here. This hydrogen environment, its own respective little peak. It has three to the right. It has one hydrogen next to it that's its own separate environment, and it has two here. So we have 6 as our n plus 1. This will give us 7, a multiplicity of 7. This is much the same, a multiplicity of 7. And let's count for these. We have 1, 2, 3, 4. This will be a 5-let. And then this as well will also be a 5-let, or whatever that would be. Not too good with those, but all right. Well, there's the solution there with their own respective multiplicities and the differing number of hydrogen environments. Moving on, we have this. Now this one's a little tricky, so bear with us here. We have a hydrogen environment here, and again, we're just going through the same process of what are the hydrogen environments of which we have. So we have one environment here, one here, one here, one here, and because there's no symmetry, it gives rise to all these different environments. So we have 1, 2, 3, 4, 5, 6. We'll get 6 signals in this molecule. Let me just double check on the H NMR spectra. Okay, now for don't want to be getting rid of that. Now we have to figure out the multiplicity. This one here is quite simple. There are no neighboring hydrogens, so it just has a singlet. This one here has 2 neighbors, so it becomes itself it becomes a triplet. Jeez. This one here has two hydrogen neighbors to the left, 2 hydrogen neighbors to the right, and that gives it a multiplicity of 5. This one's much the same. 5 there. Notice here we'll have 2 to the left, 2 to the right. That gives us a multiplicity of 5. And on this one here, we'll have a hydrogen here and a hydrogen here. Alrighty, and we know that there's 2 hydrogens, so this signal here gives rise to a triplet. Alrighty, and that's all the problems. I hope you guys enjoyed.